session for the NPTEL course Climate Dynamics, Variability and Monitoring, week 9 problem solving session. I guess I am audible. So today we will start with the atmospheric and the oceanic circulation topic. So the first question for the today. Today first we will review what were discussed in the classes of atmospheric circulation and the oceanic circulation, and then we will try to solve few MCQs based on the class content. We have seen in our class that there is a seasonal shift in the atmospheric circulation pattern. Major seasonal migration of the high and the low atmospheric pressure belts occurs, and this corresponds to the surface level and the high altitude winds, thus those are observed in our earth. At the surface level, the seasonal shift can be observed by plotting the 1000 hectopascal pressure surface altitude contours, which defines by the where the mean is 16 meter. Rate is positive for the high pressure zone. White and the blues are corresponding low pressure zones. So in this figure, the 1000 hectopascal height and the wind vectors are plotted for the two seasons. One is the January and another is the July. January is when the southern hemisphere summer, and the July is the when northern hemisphere summer. The contours intervals are of 20 meter, and the largest vector represents the wind of about 15 meter per second. Here positive values are denoted with the red color. The basic feature of this kind of plot, the season variation plot, can be explained as follows. During the northern hemisphere summer, that is in the July month, the direct vertical solar insolation shifts towards the north, that is towards the 20 degree to about 10 degree latitude zone. Hence, at that region, equatorial this low pressure belt forms, and we can say the equatorial low pressure belt shifts to 10 degree to 20 degree northern region, along with the change in the latitude of the direct normal insolation. This shift is particularly prominent over the Asian and the American landmass, which experience large heating during the summer season away from the ameliorating influence of ocean heat transport. As a result, in the summer season of the northern hemisphere, we know that the intertropical convergence zone, or the ITCZ, lies around 20 degree to 10 degree to 20 degree northern region. This corresponds to the northward shifting of subtropical highs and subpolar lows as the northern Hadley circulation moves to the north, and its descendant branch migrates to 15 to 90 degree north. In the normal case, you know that this Hadley circulation branch aims at about 30 degree north. But in the summer season, when there is a summer in a hemisphere, then there is a migration of the last branch of the Hadley cell also occurs. The polar high pressure zone weakens this time, as the polar regions are heated up during the near 24 hours daylight, and the subpolar lows are also moves towards north. Not the subpolar low are not observed in the summer hemisphere at 60 degree. The subpolar lows move at towards 75 degree to 80 degree north when there is a northern hemisphere summer. Now the southern hemisphere Hadley circulation grows strong during the southern hemisphere winter, and it expands north and extends from 30 degrees south to 15 degrees north during June, July, August season. As a result, there is a shift in the intertropical convergence zone, and the strong southeastern straight winds of the southern hemisphere now cross the equator and the flow into the northern hemisphere convergence at the ICTZ location. As they move northwards due to the Coriolis force, uh, due to in the right direction, hence they change direction and now becomes the southern hemisphere winds blowing from equator to 15 degree to 20-degree northern latitude in the season when there is a northern hemisphere summer. This winds are particularly prominent in the time over the northern Indian Ocean, because this wind converts strongly over the intense land-based subtropical low pressure over the central and the eastern Asia, and this wind is the key wind which is the for the our country's wind for monsoon, that is the southwest monsoon winds. This wind pick up moisture over the Indian Ocean and hit the south and southeast Asian land masses, resulting the heavy precipitation. The 1000 hectopascal contours and the wind directions for July over the southern South Asia and northern Africa has been shown in this figure. You can say you can see in this figure the monsoon winds are entering from the western region of our country, you can see, because and this originates as there was in summer season, and this ICTZ moved to the northern about 20 to 30 greater than 10 degree to 20 degree zone. This 1000 hectopascal contours and the wind directions for the July month over the South Asia and the northern Africa, you can say in this figure, and it is showing that the migration of the southeastern trade winds over the equator has become the southwestern monsoon wind. So the monsoon wind is really the branch which generates due to migration of the southeastern trade wind over the equator to become and becomes the southwestern monsoon winds. Similarly, when there is a northern hemisphere winter, that is in the January month, the solar insolation moves in the 20 degrees south. As a result, there is a shift to the intertropical convergence zone to the 10 degree to 15 degree southern zone, southern hemisphere, especially over the land masses like the northern Australia and the southern Africa and the South America. You can see here the what occurs when there is a northern hemisphere winter. There is also a southward shift of the subpolar low and the subtropical high pressure zones as the northern hemisphere polar high gains strengthen and extreme cold conditions develop over the regions like Siberia or the Northern America. Thus, northeastern trade wind now blow for around 20 degree north towards the intertropical convergence zone. Over southern Asia, there is these are called the northeastern monsoon wind. As the northeastern trade wind occurs across the equator, they deflected in the left region due to the left and blow from the northwestern. You can see when it crosses the equator, it now deflects towards the left and blow as a northwestern wind. You can see here in this picture. Thus, they become the northwestern monsoon wind in the southern hemisphere that blows over Indonesia and the northern Australia, bringing the rainfall in that regions. Now we will see what kind of questions or what kind of MCQ questions could be asked. Hello. Am I audible? Okay. Uh, Sorry for the being late. Sorry. So today we will solve first review few of the weekly content from this week 7 and the week 8, and then we will see what kind of MCQ questions could be asked from those contents. Now we have seen there is a seasonal shift of atmospheric circulation pattern in our earth. The major seasonal migration of high and low atmospheric pressure belt and the corresponding surface level and the high altitude winds are the main drivers which determines how our monsoon occurs, or how there is a rainfall in our continents. At the sea level, the seasonal shift can be observed by plotting the 1000 hectopascal surface altitude contours, where mean is 16 meter and the rate is the positive for the high pressure zones, white and blue at the corresponding negative values, and identifies the low pressure zones. And here the 1000 hectopascal height and the velocity wind vectors for the month when there is a northern hemisphere winter, that is January, and the northern hemisphere summer, that is July, has been plotted. Here in this plot, the every contoured intervals is at 20 meter, and the largest vector represents the wind of about 15 meter per second, and the largest wind has been given with the reddish color, the more reddish color. Positive heights are here in red, you can see. The basic feature of this kind of seasonal variation plot can be explained as follows. During the month of July, when there is a northern hemisphere summer, the direct vertical solar insolation shifts to the northern latitudes, that is about 20 degree or degree to 10 degree latitude. Hence, the equatorial low pressure belt also shifts to the 10 degree to 20 degree northern zone, along with the change of the latitude of the direct solar normal insolation. This shift is prominent over the Asian and the American land masses, which experiences large heating during the summer, away from ameliorating influence of oceanic heat transport. As a result of such kind of direct insolation in the northern hemisphere, when there is a month of July or the northern hemisphere summer, the intertropical convergence zone lies around the 10 degree to 20 degree northern region. This corresponds to the northern the northward shifting of subtropical highs and the subpolar lows in the northern Hadley circulation moves to the north. And we know in the normal case the Hadley circulation's descending branch ends at about 30 degree north, but when there is a summer, the descending branch of the northern Hadley cell will end at about 45 to 50 degree north. Also, the corresponding polar high pressure zones weakens as the polar regions are heated up during this time for near about 24 hours, and the subpolar lows, which is normally seen at 60 degree that also shifts the upward region about 75 to 80 degree north during the summer time. Now, when in this time, southern hemisphere Hadley circulation grows stronger during the southern hemisphere winter, and it expands to the north and extends from 30 degrees south to 15 degree north during the June, July, August season. As a result, there is a shift of the intertropical convergence zone. The strong southeastern trade wind of this southern hemisphere now can cross the equator. because the southern hemisphere Hadley cell now has been shifted to about 15 degree north, and this southern hemisphere southeastern trade wind in the south of the southern hemisphere now can cross the equator and flow in the northern hemisphere to converge at the intertropical convergence location. As they move towards the north, they will now be on the effect of the Coriolis force, which will drive them to the right of their flow. So they change in direction. They change their direction and becomes the southwestern trade wind. Southwestern winds blowing from the equator to the 15 degree to 20 degree northern latitudes. You can see this conditions of this figure. Here is the branch of the southeastern trade wind. It now in the July month it crosses the equator, and due to the Coriolis force effect, now it bends towards the south. Now it becomes the southwestern wind. These winds are particularly prominent over the northern Indian Ocean because the wind converts strongly over the intense land-based subtropical low pressure over the central and the eastern Asia, and this now this wind is called the southwest monsoon wind, and this wind is the main cause of the monsoon or the precipitation in the Southeast Asian land masses and also India. The 1000 hectopascal contours and the wind direction is clearly shown in this figure. You can see this is the monsoon branch, and this generates due to the migration of the intertropical convergence zone, which occurs due to the direct solar insolation of the in the northern hemisphere summer. Similarly, when there is a northern hemisphere winter, the vertical solar insolation now moves to the 20 degree southern latitudes. As a result, there is a shift of the intertropical convergence zone to the 15 degree to 10 degree those southern latitudes, especially over the land masses like the northern Australia, southern Africa and the southern America. There is also the southward shift of the subpolar low and the subtropical high pressure zones at the northern hemisphere. Polar high gain strength and the extreme cold condition develops over the Siberia and the northern America. Thus this northeastern trade wind now blow from around 20 degree north towards the south to the southern intertropical convergence zone, where it is now situated. Over the southern Asia, this wind is called the northeastern monsoon wind. As the northeastern trade wind cross the equator, it also affects a left towards left force due to Coriolis effect and blow from the northwest. This thing is shown here. As it crosses, you can see this wind was originated from the 20 degree to 20 degree northern hemisphere, but now as it has been moved, now it will you have to go to intertropical convergence zone. Now you have to cross the 0 degree latitude. When it crosses the 0 degree latitude, it will be deflected towards the left. So this is known as the northeastern monsoon wind, and this northeastern eastern monsoon wind it becomes the northwestern monsoon wind. Thus it becomes the northwestern, and this northwestern monsoon wind is the main cause of precipitation over the Indonesia and the northern Australia, which you know these are here. It will bring precipitation here, these zones. Now we will solve a few of the questions using this discussion. You can unmute yourself or you can write in the chat box. So now the first question for today is December, January, February, that is when there is northern hemisphere winter, the sea level in this December, January, February, the sea level wind pressure map, which hemisphere shows stronger subtropical high? Northern hemisphere, southern hemisphere, both equator, both equal, and the equator. In December, January, February, sea level wind or pressure map, which hemisphere shows the stronger subtropical high? Stronger subtropical highs are seen in the summer hemisphere. So, stronger subtropical highs are seen in the summer hemisphere because it is linked with the solar insolation. More solar insolation is more solar insolation imply stronger subtropical high. So in the December, January, February, the more solar insolation occurs at the southern hemisphere. So question 1, option B is correct. You can unmute yourself. Am I audible? Uh, am I audible? Uh, the next question is in the June, July, August, or when there is a June, July, August, that is in the northern hemisphere summer, the equatorial low shifts where 20 degree to 30 degree north, 10 degree to 20 degree north, 0 to 0 to 5 degree south, and stay fixed at the equator. We have seen in this figure that B, yes, the equatorial low is directly linked with the solar insolation, and the solar insolation shifts this equatorial low to 10 degree to 20 degree north. Question 3 is the northern hemisphere Hadley cell is strongest during which month? The December, January, February, March, April, May, June, July, August, and September, October, November. The Hadley cell becomes strongest when there is a summer hemisphere. Yes, C. Yes. In the summer hemisphere, the Hadley cell becomes strongest. So option will be C. Question 4. In the mass stream function diagram, the cell is strength is proportional to The value of stream function, gradient of stream function contours latitudes only and the pressure levels. In mass streamline diagrams, that is this kind of diagrams, this height and wind vector diagrams, this kind of diagrams are known as the stream function diagram because it gives how the strength of some vector quantity. uh, Here the cell strength is proportional to what? Value of stream function, gradient of stream function contours, and the latitude only, and option B is pressure level. For the question 4, the this kind of vector, this kind of contour diagram, always there is a gradient of this function is proportional to the cell strength. Question 5. In the subtropical jet cross section, in the subtropical jet cross section, the maximum zonal wind occurs near where? The 30-degree latitude, 12 kilometer, 10-degree latitude 6 kilometer, 60-degree latitude or 2 kilometer, and the equator or the 15 kilometer. That is where the subtropical jet is located. This question is where the subtropical jet is located. 10-degree latitude 6 kilometer, 30-degree latitude 12 kilometer, and 60-degree latitude 2 kilometer, and equator and the 15 kilometer. We know the subtropical jets are generated over the end of the troposphere, and this is subtropical, and this is question 5, option B is correct. Now question 6. Now question 6. Intertropical convergence zone shifts north in the boreal summer because stronger Coriolis effect, maximum solar heating at 15-degree north, polar jet shift, and the ocean upwelling. We have seen in this discussion today that the intertropical convergence zone shift is linked with the maximum solar heating, which occurs in the boreal summer or the northern hemisphere summer. The two main thing, two similar thing. The heating occurs near the 20-degree northern region, so the maximum solar intertropical convergence zone shifts at that zone. Question 7. Southeast threats cross equator in the June, July, August and becomes the southwestern monsoon wind. This occurs due to which effect? Gravity, Coriolis force, deflection of the southeastern winds towards in the right direction in the northern hemisphere, and for C is the pressure gradient reversal, D is the centrifugal acceleration. Question 7, of course option B is correct. As the Coriolis force deflects southeastern trade wind when it comes to the northern hemisphere, the southwestern monsoon winds get formed. Question 8. Asian monsoon are more stronger than African because of larger continental heating, higher latitude, more ocean influence, and option D is the weak Coriolis force. Asian monsoon is more stronger than the African monsoon because of what? Larger continental heating, higher latitude, more ocean influence, and option D is the weaker Coriolis force. Question 8, option A is correct. For the larger continental heating, Asian monsoon is more stronger? Question 9. The northeastern trade wind crossing equator in the December, January, February, when there is a boreal winter, becomes the northwestern monsoon wind in the southern hemisphere. This occurs due to what? Frictional heating, polar islets, polar easterlies, strong ferocity, and the leftward Coriolis deflection in southern hemisphere. Question 9, of course, this is the similar thing of question 7. The northeastern trade wind becomes the northwestern monsoon winds in southern hemisphere because of the leftward Coriolis force deflection when it crosses the southern hemisphere. Question 10. The continental heating intensifies monsoon because it enhances the intertropical convergence zone shift, weakens Coriolis, reduces friction, and increases polar heating cooling. Continental heating intensifies monsoon because it enhances intertropical convergence zone shift, weakens Coriolis force, reduces friction, increases polar cooling. For question 10, option A is correct. Continental heating is directly linked with the heating intense continental heating is directly linked with the intertropical convergence zone shift. Question 10, option A correct. Now in this lecture of week 7, we had seen about the mean latitude eddy circulation system. The Ferensel, which is in the mid latitude zone, that is about 30 to 60 degree, is weak and thermally indirect. That is here the cold air rises up and the hot air dips down, and hence does not contribute to this Ferensel circulation, does not contribute to the heat transport from the low to high latitudes. The polar transport of the sensible heat is instead accomplished by the deviation from the zonal average or the eddies, which are observed as repeated fronts of anticyclonic high and the cyclonic low pressure that migrate through this mid latitudes as weather fronts. The mean quantity x delta and the zonally average quantity x bracket and the zonal average zonal average vector quantity x bar bracket has been shown here. Here the temporal fluctuation has been defined as the x dash is equals to x minus x bar, and the eddy fluctuation has been defined with the x star. X is any quantity, and the zonally average temporal fluctuation can be written as the bracket of this temperature fluctuation equation. The eddy fluctuations are defined as the deviation from the zonal average for the given latitude and for a given pressure surface. The eddy velocity fluctuations are written as the following: the zonal eddy velocity, that is u minus u bracket, and in the zonal direction, that is west to east, and the meridional from the south to northern direction, the eddy velocity is v star, that is written as v star is equals to v minus v bracket, where the v bracket is the zonally average quantity. Any bracket thing is the zonally average quantity, and x v is the any quantity, or x or v or u is any quantity itself. However, in the mid latitude region, The zonally average meridional velocity is closer to 0. That is, thus here we can use the V bracket to be 0. Hence we have the eddy fluctuation in the meridional direction, or the eddy velocity in the meridional direction is equals to V, and the entirely of the meridional velocity component is contributed by the eddy fluctuation, and the zonally average velocity is entirely in the zonal direction given by U bracket. The formation of storm fronts and the corresponding poleward heat transport occurs in a cyclic process, which process is known as the index cycle. This cycle begins with a steady and the uniform westerly wind with a large U bracket, or in the which has a large velocity, zonally average velocity U bracket, and the small eddy fluctuations which are defined by the U star and the V star. You have seen in the here that there is no meridional average, zonally average meridional velocity is 0. So index cycle have no effect of this V bracket. It has only effect of the U bracket, which is in the zonally average velocity. This cycle begins with a steady and uniform westerly wind with large U bracket and small eddy fluctuations which are U star and the V star blowing along the latitudes between the subtropical highs and the subpolar lows. Then, due to the local variations in insolation, the local spots of high and the low pressure intensify on the outer boundaries of the flowing westerlies. Lows and high is create CCW, or circular wind pattern, or CCW and CW circulations around them due to the geostropic balance, and this circular and anticyclic and anticyclic wind circulations around them due to the geostropic balance, and this impart eddy fluctuations in the zonal and the meridional directions on the following westerlies, causing the winds to curve in the north then to south direction. Due to lack of direct heat transport across this mid latitude, that is within 30 to 60 zone, this high and low pressure zone intensify over time, adding more curvature and the eddy fluctuations to the wind flow. Thus the wind pattern develops wave-like structure, and this wave has a name that is known as the Rossby wave. With subpolar low pressure migrating from the southwards, and the subtropical high pressure migrates from the migrates to the north direction. The amplitude of these waves continue to grow, and eventually this high and the lows pinch of form the primary pressure belts, creating cut-off cyclonic lows and the anticyclonic highs that migrate in the opposite direction in the opposite direction. The northward moving highs bring dry warm weather, while the southward moving lows bring cold and the stormy weather in the mid latitude zone. They are meridional migration transport heat from the subtropical to subpolar, that is 30 to 60. Eventually the cutoff high and the low dissipate away, and the index cycle begins anew. Here the schematic diagram for the index cycle has been seen, and also the meridional transport of heat by eddy fluctuation occurs is particularly prominent in winter, when the large temperature differentials exist between high and the low latitudes. So different key points in this two lecture slides or the this lecture materials, which we will try to set a few MCQs with this two-page lecture material of the mid-latitude eddy circulation. So the main key thing is the mid-latitude eddy circulation. This occurs to the eddy formation, and here and the main thing for occurring this is the as the Ferrel cell is very weak, and there is a thermally and it is the thermally indirect. It cannot directly transport heat from the 30° to 60° zone. So here the one cycle of one index cycle forms where the storm forms and the corresponding poleward heat transport occurs in a cyclic process. This cycle begins with steady and uniform westerly wind with a large zonal velocity time mean quantity u bar, and small eddy fluctuations feature Wister and Easter. Then, due to the local variation of insolation, the local spots of high and the low pressure intensify on the outer boundaries of the flowing westerlies. Lows and the highs create the circular and the clockwise and anti-clockwise circulation around them due to the geostropic balance, and this impart the eddy fluctuation in the zonal and the meridional direction on the flowing westerlies, causing the wind to curve in the north and to south direction. Now another key thing is this mid-latitude transport is more prominent when there is winter in the hemisphere, because then the large temperature differential exists in between high and the low latitudes. Now the main questions from this lecture slides can be like this. Eddy fluctuations, that is Wister is equals to V in the mid latitudes, because what is this? V bracket is equals to 0, U bracket is equals to 0, Coriolis negligible, friction dominates. You can write the thing in the chat box, or you can unmute yourself and tell the answer.
Option A.
Yes. Question 11, option A is correct. Question 12, index cycles begins with weak easterlies, uniform strong westerlies, strong trade wind, and the polar jet breakdown. Index cycle begins with the uniform strong westerlies. Question 13 is Rossby webs grow and break into cutoff low or high because of increase of the pressure gradient force, amplifying the eddy fluctuation, strong friction, and the hydrostatic imbalance.
Option D.
No, this is option B. The Rossby webs grow and break into the cutoff low and high because of the eddy fluctuations. In the December, January, February, the zonal mean width cross section is still dominant. Equator surface, pole troposphere, subtropic stratosphere, equator stratosphere. In December, January, February, easterlies dominate. I have to see the question answer. Zonal mean wind cross section, easterlies dominate. Equator surface, pole upper troposphere, subtropic stratosphere, and the equator stratosphere. Easterlies is a surface wind. The option A would be correct, I guess. But in the December, January, February, the equator is still is dominant in the equator and surface. Question 14, option A is correct. The easterly is not seen in the upper stratosphere or upper troposphere or stratosphere. Easterly is a surface wind. It is a low level wind.
Okay.
Yes, question 14, option A is correct. You have to, when there is upper lower the layers are given, you have to say we can check which branch it's originate, the easterlies or westerlies its originate. If there is that kind of combination, you can mark the answer. Question 15, the 1000 hectopascal pressure wind plot, which was done in the boreal summer, June, July, August over Asia, has strong southwestern monsoon wind due to northward intertropical convergence zone, polar high, Ferrel cell strengthening, and the Rossby webs.
Option A.
Yes, of course, question 15, option A is correct. The southwestern monsoon winds originate from the as the the westerlies from the southern hemisphere now can go up to cross the equator, and it reflects in the right direction. In the July wind map, the southeastern trade wind cross equator and bend. Question 16b. This similar question in the 15. It bends rightward and creates the southwestern monsoon winds. Question 17. In the January wind map, northeastern trade wind crosses equator and bent in which direction? Leftward, northwestern monsoon wind. Rightward, northeastern monsoon wind. Straight south, eastward jet stream.
Option D.
No, this is when there is a January wind map. The northeastern trade wind now crosses the equator and bends in the leftward direction, and now it becomes the northwestern. This figure, this January,
Yes, ma'am.
this crosses, this was coming here, but when it's crossing this 0 degree, it is bending, and the northwestern monsoon wind it is creating, and it is the the monsoon season of the Australian continent, you can see.
Excuse me, ma'am.
Yes.
In the final exam, these pictures will be given, or we have to rewind it?
I do not know about how will be this final exam pictures will be given. I was just for the making MCQ, I was suggesting those pictures because in some time the pictures shows what is what is taught in these classes. You can see here they have this thing, and also the pictures show
Yes,
the
madam.
thing. Yes. I do not have exactly can tell about how will be the final exam setup.
Okay.
Okay. You can ask this when if there will be any picture based question or something. But for the for one MCQ, you were asked some picture based question, I guess. In some week MCQ, you were asked some picture based question. Question 18 yes. Question 18, in July 1000 hectopascal charts, which region shows the strongest monsoon lows? North America, Central Asia or India, Southern Africa, and South America. Strongest monsoon low is seen when there is of course in the monsoon season, or before the monsoon there is a monsoon low. So for the Central Asia and India, this thing, the strongest monsoon low is seen in the June, July, August. You can see here in this plot. strongest monsoon low. You have to find.
What is the meaning of strongest but monsoon low? Low means?
Monsoon low is, I guess, monsoon low here is the thing when there is a low pressure zone over the continent.
Oh, low means low pressure zone.
Yes.
Okay.
Low pressure, as there is before the in the summer month, as there is low pressure zones over the this continent, Central Asia or India. Now here the southeastern trade wind now can blow towards the high pressure zones to that low pressure zones and create the monsoon wind. Uh, from that sense, the this kind of strongest monsoon low is linked with the coming monsoon. So in the in the July, the coming monsoon is will be in the Central Asia or India. So question 18, option B is correct. Today we will now solve this ends the lecture for the week 7 contents. Now we will see about the week 8 contents. We will not go to week 9 contents today. So the first question for the week 8 content, or the content on the oceanic circulation, is this: the average salinity of open ocean water is closest to what value? 31%, 34.7%, then is 37%, and that is 40%.
37%.
This is option B correct. This is 34%.
Okay.
All these questions were just from the MCQ, from the material itself, so you can just check the value. What ion contributes most to the ocean salinity? Potassium, sulfur dioxide, so 4 ion, sodium Na plus, and the magnesium 2, Mg2 plus.
Sodium.
Yes, sodium contributes most to the ocean salinity. Question 3. Why do polar regions lack the strong thermocline? We know the ocean has 3 layers. First is the mixed layer, which is affected by the circulation of atmosphere or any interaction of the atmosphere. The surface wind of the surface level winds of the each cells. And second is the thermocline zone, which is about 1000 meter up to depth, and 1000 to 3700 meter about, or 3.7 kilometer, or that range. There is the deep layer. We have seen that in the polar region lacks strong thermocline. This is because the high solar heating, low precipitation, surface temperature, and the density approach deep water values, and high salinity stratification.
Option C.
Yes, question 3, option C is correct. As the surface and density approach to deep water values or to the 0 degree Celsius, at the here this region lacks strong thermocline. Question 4. Compressibility effects are removed by plotting virtual temperature, potential temperature, and the density, mean salinity, and the sea level anomaly. Question 4. It has been seen in this figure that the sea water is slightly compressible for the high pressure found in the deep ocean. This compressibility effect by itself will change the density and the temperature of the sea water with depth. To remove such compressibility effect, usually the potential temperature and the potential density profiles are plotted for the sea level water with depth. For the sea water with depth, potential temperature and the potential density are the values a parcel of sea water at a given depth z will have, if the parcel is adiabatically brought to a chosen reference pressure, usually 1 bar pressure, from its original pressure to the depth of z. So here in this oceanography, there is the potential temperature and the potential density concept, which is similar to the air, but here the parcel, you have the parcel of seawater, and this parcel of seawater has been adiabatically brought from to a chosen reference pressure, that is about taken usually 1 bar pressure from its original pressure uh, at the depth of z from the surface. So question 4 option question 4 compressibility effect are removed.
Option B.
Yes, question 4 option B is correct, potential temperature and potential density. Question 5, at subtropical latitude, surface salinity is observed to be high because precipitation is greater than evaporation, river runoff dominates, evaporation is greater than precipitation, and option D, sea ice melting.
Option B.
Option B. Question 5. Uh, I guess this will be option C. As in the subtropical latitude, evaporation is greater than the precipitation, the surface salinity becomes high.
Okay.
Now question, here the salinity profile during the month of February for the various location has been seen with the MIMOC data. Here the salinity profile of the deep layer, you can see, is nearly constant irrespective of any latitudes, you can see, and it is almost identical to the surface salinity values found in the high latitudes, as most of the deep layer water comes from the surface water that sinks at the few locations at high altitudes. High latitudes. Subtropical oceans show large salinity gradient in the thermocline region. There are also marked the differences in the salinity values of the mixed and the thermocline layers between the oceans. The Atlantic Ocean is saltier than remarkably saltier compared to the more open Pacific, because the ocean as the former is surrounded by the continent with large amount of salt runoff from the land. Now in this oceanic circulation, we have seen the plot of the potential temperature and salinity and the potential density as a function of pressure and the latitudes. Here the potential temperature has been shown with degree Celsius contours, and the salinity is been given from the percentage, and the potential density has been given with the kg per meter cube SI unit, and the pressure has unit of the decibar, which is 1 decibel is equivalent to 1 meter of depth, and the latitude for the Atlantic and latitude is given usually in degree. And
Excuse
here,
me, ma'am.
yes,
Between latitude 60 to 80, there is a white spot, right? White strip, 60 to 80.
60 to 80. Okay.
Right hand side, Pacific Ocean.
Pacific
Between
Ocean.
60 to 80.
60
The
to
right
80.
side. In between 60 to 80, 60 to 70, the white spot.
This white spot
strip.
you were saying?
No, right
this.
side. This one.
This. Okay. Is there continent? I have to check. I have not seen that. Maybe there is continental continent. Here there is 80 degree above. There is some white spot. Yes, I will check that. Why this white spot is.
Okay,
I
ma'am.
presently I do not know the thing. Here the plots of the pressure, the potential temperature, potential density and the salinity has been shown against pressure and the latitude for the two ocean, Atlantic Ocean and the Pacific Ocean. Contours of potential temperature, salinity and the potential density for the above standard freshwater density of 1000 kg per meter cube are plotted for the Atlantic and Pacific Ocean with respect to the pressure above the sea level. In this plot, y-axis is in the decibel unit above the sea level pressure. The pressure in the decibel unit is a root proxy for the depth, as 1 decibel increase in the pressure corresponding to increase of depth of about 1 meter. From this figure, you can see that the temperature gradient between the surface and the deep layers are relatively large in between 50 degree to 50 degree north to 50 degree south latitudes. Here you can see at the higher latitudes the gradients are relatively flat throughout the depth. Large salinity gradient exists in the northern and the southern subtropics, that is within 35 to 10 degree, where 35 to 10 or 10 to 35 degree, where the top 500 meter have high salinity values. This is especially true for the Atlantic Ocean, where the high salinity extends up to 1000 meter even. In the extratropics and the near the poles, this situation is reversed, as the fresh water exists in the top 300 meter. The salinity actually increases slightly at the greater depth. In the tropics, subtropics and the mid latitudes, up to that is up to 55 degree latitude, the top 200 meter oceanic layers have low density than the bottom layers. This driven by the high surface water temperature at the tropics and subtropic and the low salinity of the surface water at the mid latitudes. This prevents mixing of water from the top layer and the bottom layers for low and the mid latitude ocean. The segregation of the top layers from the bottom layers between the equator and the mid latitude also explains the steep thermocline in this region, as colder water from the deep layer cannot rise up in this case and mix up with the top water layer, which is less saline water layer, that is heated up by the absorbing solar radiation. In contrast with the density gradient are nearly uniform in the high latitude. In contrast, density gradients are nearly uniform in the high latitude. The surface water near the polar regions are fresh from the excess precipitation over evaporation and strongly cooled by wind and the radiation losses. Hence, their temperature and the density approaches to the deep ocean levels. Hence, the high latitudes. In the high latitude, we observe the efficient bouncing and the induced mixing of the ocean layers. This also creates a flat temperature profile with depth in the polar region. Thus, the upwelling of the deep ocean layers waters and downwelling of the surface water primarily happens in the subpolar region, that is within 70 to 80 degree latitudes. Now we have the few questions from this slide. So now the question 1 or the question 6 from of this oceanic circulation is: Atlantic Ocean is more salty than Pacific, mainly due to what? high solar insolation, more salt runoff and higher evaporation, lower
Option B.
precipitation, and the option D is shallower depth. Yes, question
Option B.
6, option B correct. The more salt runoff and the higher evaporation is the cause of the saltiness of the Atlantic Ocean. Question 7, density driven circulation is most effective where? Subtropic, higher latitude, tropics, and the equator.
Equator.
No, question 7, density driven circulation, that is driven by the upwelling of the deep layer waters and the downwelling of the surface water primarily happens in the subpolar region, that is within the 70 degree to 80 degree north 80 degree latitude of it.
Okay.
So higher latitude have the more density driven circulation. Question 8a, true or false, just mark it. In a salinity profile, the deep ocean salinity is nearly uniform because it originates from the higher latitude surface water that sink. Is this statement true or false? In the salinity profile map, the deep ocean salinity nearly uniform because it originates from the high latitude surface water that sinks. Question 8 is true. This statement is true because of the density driven circulation, this deep ocean salinity becomes uniform. Question 8 true.
True. Yes, ma'am.
Yes. Question 8b, at the 1000-meter depth, that is when there is a thermocline is stopping, the tropical ocean temperatures are typically what? 20 degrees Celsius, 10 degrees Celsius, 4 to 5 degrees Celsius, and 0 degrees Celsius. Question B, at the 1000-meter depth, the tropical ocean temperature becomes what?
10 degrees centigrade.
No, this becomes 4 to 5 degrees Celsius.
4 to 5, okay.
Yes, when there is thermocline is when there is deep ocean, deep layer is starting and the thermocline ends. At the tropical region, there you will find temperature of about 4 to 5 degrees Celsius. But when there is the polar region, you will find there the 0 degrees Celsius.
0 degrees Celsius.
Yes.
Yes.
Question 9. The high salinity in the subtropical water exceeding 2000 meter is most typical of which ocean? Pacific, Atlantic, Indian, and the Southern.
Atlantic.
Yes, question 9b is Atlantic. The high salinity of the subtropical water exceeding 1000 meter is typically observed in the Atlantic Ocean. Question 10a. The average mixed layer depth globally is how? 20 meter, 70 meter, 200 meter, and 500 meter.
Centimeter.
Yes, this is 70 meter. Question B, true or false? Mark it. Mixed layer thickens in winter high latitudes because weak surface cooling and convection depend it. True or false? This statement is false. You can check from your notes. I will not discuss it now. The mixed layer thickens in the winter high latitude because weak surface cooling and convection depend up. This is not weak. In the higher latitude, there is a strong surface cooling and convection which depend it, not the weak.
Yes.
Question 11. Upwelling region typically have mixed layer depths, less than 30 meter, for 70 to 100 meter, 200 to 500 meter, and greater than 1000 meter.
Option A.
Yes, where there is a upwelling region, you will find the mixed layer will end at 30 meter. So the mixed layer is less than 30 meter. So in the upwelling region, the mixed layer is lesser than the normal 70 meter. Question 12. Effective heat capacity of ocean mixed layer is how many times of atmosphere? 3 times, 10 times, 30 times, or the 100 times? Effective heat capacity of ocean mixed layer is how many times of atmosphere? Question 12, option C is correct. You can check from the note that
Okay, ma'am. 30.
this is 30. Question 13. The mixed layer responds rapidly to what? Solar cycles, which is typically in the sunspot variation, the volcanic eruption, seasonal winds and heat fluxes, and the plate tectonics, which influences the mixed layer
Option
most
C.
rapidly. Yes, question 13, option C is correct. Here the mixed layer depth has been shown with different time, that is the boreal summer and the boreal winter and the boreal summer. You can the turbulent mixing process are driven by, in the mixed layer, the turbulent mixing process are driven by supply of kinetic energy from the wind and their interaction with the waves on the surface of the ocean water. This turbulent mixing process is very efficient and are particularly strong in the region of high winds and waves. In the high latitudes, the ocean surface is cooled very strongly, creating cold, dense water near the surface and generated buoyancy force that forces that those forces drive convective overturning with the sinking of cold water and rise of warm water in the mixed layer. So the mixed layer in the high latitudes and in the winter are usually thicker. At the low latitudes, in the summer, the ocean surface is cooled very weakly and may be warmed by strong surface absorption of radiation. Then, surface water are less dense and deeper waters less dense than the deeper waters in the mixed layer, and the buoyancy driven overturning, where the high warm water will sink down. The cold water will sink down will not happen. So, mixed layer in the lower latitude during the summer are usually warm and thin. So, the key points are the mixed layer in the higher latitudes in the winter season or in the winter are usually thicker. Mixed layer in low latitudes or during summer are usually warm and thin. Other factors to consider for upwelling or downwelling of water is the salinity gradient. High evaporation rates increases the salinity of the surface water, as the only the wind the can only the water can evaporate. The salt is left on the ocean bed, and making them denser, and hence encourage the convective overturning. In contrast, supply of fresh water, that is precipitation or the glacial or the river runoff, decreases surface water salinity and suppresses overturning. So you know the more saline water contains more salt, and this is denser, so it will go deep. it will dip. The depth of the mixed layer is hence quite variable due to salinity also. Its average depth of salinity is average depth of the mixed layer is 70 meter, but its depth may be as small as a few meters in the region where the deep water upwells near the equator and or in the eastern boundary currents to more than 500 meter in the regions where saline surface water sink down to the bottom of ocean. The mixed,
Excuse me, ma'am.
yes.
River runoff increases or decreases the salinity of ocean water?
This decreases salinity water, surface salinity, because
it is always decreasing. River runoff.
This is always decreasing in water supply.
Because in Atlantic Ocean, river runoff said that river runoff increases the salinity in Atlantic Ocean.
Okay. I have to make this. I have to make this clear. I could not answer this right now, I guess.
Okay, ma'am.
So the here the mixed layer depth profile and the temperature profile for the January and July has been shown. The contours are the 30 decibels interval, with the reddest contour to be the mixed layer depth less than 30 decibel. The deep blue region of the map are the places where large scale downwelling of surface level water occurs and are located during the winter times at the high latitudes. This is the map for the mixed layer depth map. You can see there is the while large scale downwelling occur, those places has been given to be those places has been shown in the blue color, and this the downwelling of the water level occurs in the southern hemisphere. You can see when there is a southern hemisphere time, this downwelling of surface water occurs in the ocean. But when there is in the winter time, here you cannot see the downwelling of surface water because here there is no ocean, but here is some small ocean you can see. So downwelling of the downwelling at higher latitude is observed when there is a winter hemisphere. Much of the short and the medium term climatic influence of the ocean is confined with the process of the occurring in the mixed layer. Storage and removal of heat on the time scale is less than a year are confined to the mixed layer. The mixed layer responds fairly quick to the changes of surface wind and the surface temperature, whereas the ocean below the mixed layer, such as deep layer or even thermocline, does not respond to this wind velocity thing. The figure here shows the potential temperature contours with this various season. The contours are at different interval of 2 degrees Celsius, where the warmest contour has been shown with the more redder color. The thermal capacity of the mixed layer can be considered to be the effective heat capacity of ocean on the time scale of the years to decade, and it is approximately 30 times capacity of the atmosphere. Now we will have some more questions from here. Salinity increases at the surface where evaporation of the ocean leads to what? Stable stratification, convective overturning, reduced mixing, and Ekman pumping.
What is Ekman pumping?
Okay, so now this different terms. You know this for this question, salinity increase at the surface due to evaporation leads to the convective overturning when the more dense water will dip in the ocean and or the downwell in the ocean. Now, this stable stratification occurs when lighter water overlies dense water. That is the occurs in the rainfall or river input, where the fresh, less dense water caps saltier than the saltier water below. Suppresses this stable stratification suppresses vertical motion of water and reduces mixing. This is not the case here because evaporation makes the surface water denser, not the lighter. Question B, this is the convective overturning is the main is the answer here. The reduced mixing happens when density stratification is stable, lighter above and the denser below. Here the surface freshening from the rainfall or ice melt increase stratification and isolating the mixed layer from the deep layer. This is not caused by the evaporation driven salinity increase, and this Ekman pumping is a wind driven process not directly linked with the salinity. Ekman transport which pushes the Coriolis Ekman transport pushes surface water sideways, convergence or divergence zone. Convergence causes downwelling and divergence causes upwelling. Indirectly evaporation here evaporation is not the we will discuss the Ekman pumping in the El Nino chapter once again. So here for now you can think this Ekman pumping is the due to is linked to a wind driven process which pushes surface water sideways and convergence to and the divergence zones, and the convergence causes downwelling and the divergence causes upwelling, which are known as the Ekman pumping. We will discuss Ekman pumping in the later, I guess.
Okay, ma'am.
Yes. Question 15. At the equator, mixed layer depth is shallower because of what? High evaporation, strong insolation, persistent upwelling, ice formation. At the equator, due to this
Option B.
I guess option C is correct.
Persistent upwelling.
Yes.
Okay.
Due to persistent upwelling, the mixed layer depth is shallower. Question 16. Seasonal change. The mixed layer is shallower in where? Winter mid latitude, summer tropics, winter polar, all regions. Mixed layer will be shallower in the tropic zones when
Summer
there is
tropic.
a summer tropic summer in the hemisphere. We will not discuss this now. We should discuss this. Water and the ocean, both the two systems are not separated. They are both linked, and thus you are getting this wind driven circulation patterns and the surface currents. So the transfer of momentum from the winds to the ocean currents play a critical role in driving the whole climatic system of Earth. This is particularly true for the currents near the ocean surface, which are driven by the surface winds that transfer momentum into ocean due to frictional acceleration. The uppermost ocean layer of ocean, that is mixed layer, is dragged by wind driven frictional force with driven friction acceleration, in turn drags the layer below. However, this frictional acceleration weakens with the depth, and at the base of the well mixed layer, it's where the frictional acceleration effect becomes zero. So when suppose there is, so it will just act like frictional force, and it will just go to zero at the depth. The depth over which wind-driven surface currents are generated are known as Ekman layer, after the V.W. Ekman, who developed the essential physics describing how the surface currents would form in the ocean. Consider the case where the westerly wind, that is the wind which is blowing from west to east direction and have the zonal velocity u greater than 0 over the ocean. As a result, you know the as a result, the frictional drag, a west to east moving surface current will result. You know the Coriolis force formula now. The F Coriolis is equals to mf. F is a Coriolis factor which have the phi dependence term, which is the latitude term, and the v I cap minus u j cap, and the velocity of this wave is v I cap plus u I cap plus v j cap is the velocity of the wind, and the Coriolis force on that wind is in F into v I cap minus u j cap. This u and v will interchange here, you can remember. The phi is the angular velocity of Earth's rotation. Typical its value is 10 to the power minus 5 into 7.29. If the ocean current have the plus u, that is it has the zonal direction positive west to east, it will result in development of Coriolis force at the minus fu in the meridional direction. In the northern hemisphere, if a value is greater than 0, hence this force will be on the north to south direction. This means it will be deflected to the southward, that is right to its flow. But in the southern hemisphere, if such zonal velocity that is u greater than 0 exists, as f is less than 0, this will deflect towards the left, that is it will move towards the leftward, which has been shown clearly in these figures in the southern hemisphere and the northern hemisphere. Now this surface current will drag the water layer below it immediately. Once again, the Coriolis force will act in the second layer, whereby the flow of the second layer is deflected right of the first layer in the northern hemisphere and left of the first layer in the southern hemisphere. This effect will continue downward to the each successive layer with ever in the decreasing velocity magnitude, and what we get a clockwise spiraling current with depth in the northern hemisphere and an anti-clockwise spiraling current with depth in the southern hemisphere. These spirals, which are generated for the drag effect of the atmospheric wind and the Coriolis effect, are known as Ekman spiral. You have seen the Ekman spiral plot in the northern hemisphere, and it deflects any ocean current to the clockwise direction. This spiral ends at the bottom of the mixed layer, where the contribution of this frictional force drops to 0, and the net effect of water is transported at the direction 90° to the right of the wind in direction in northern hemisphere and 90° left of the wind direction in the southern hemisphere. One can write also the general momentum equation, which was discussed in the previous slides. Applying the general momentum equation for a parcel of water in the mixed layer, Under steady state assumption, that is the dvdt, the total derivative, that is derivative with respect to time and the spatial direction, x y, for the two directions, v zonal and the meridional direction, is equals to 0, and the setting the pressure gradient force to be negligible small within the mixed layer, one can have these two equations where the frictional force balances the Coriolis force. You know that this kind of where the frictional force balances the Coriolis force. Ffx and Ffy are the zonal and the meridional component of the frictional force, and Ve and Uv are the zonal and the meridional component of the Ekman velocity for the parcel of water in the mixed layer. Here we have equated the Coriolis term with the frictional drag term. The net frictional drag force experienced by the water in the zonal direction, that is x direction, and the meridional direction, that is y direction, uh, uh, is different, and in the x direction, parcel of water in the x direction is the frictional drag force experienced by the parcel of water in the x direction is proportional to the difference between x component shear stress between top and the down bottom surface of this box, or this layer of water. Uh, Hence, the zonal component of frictional drag force will be proportional to the vertical gradient of zonal shear stress tau x. Similarly, the meridional component of frictional drag force is proportional to tau y, and these two equations can be written, and this can be put to this 9.1a and 9.1b, and now one get the equation of the Ekman velocity in the zonal direction and the Ekman velocity of the meridional direction. Note that the vertical heights has been kept with the z is equals to 0 on the at the sea level, and it is negative downward. Assuming that the density of water is constant throughout the mixed layer, we can integrate the above expressions from the top of the ocean, that is the z is equals to 0 surface layer, and the tau x is equals to tau x s, tau y is equals to tau y s, to the bottom of the mixed layer, where z is equals to z will be h and the tau x and tau y would be 0, to give a vertically integrated Ekman velocity flux. So one can write this vertically integrated Ekman velocity flux just by integrating from z from minus h to plus 0, that is in the vertical direction integration we are doing, and one can get a torque kind of thing, k cap cross tau term here, a component of k cross tau. Note that the integrated velocity flux is perpendicular to the direction of the surface shear stress.
Excuse me, ma'am.
Yes.
What is H? Minus H?
Minus h is the depth where the mixed layer is stopped, and there is no effect of the tau x and tau y here,
Okay.
at the bottom of the mixed layer. Here you can see this tau x, here there is air, and tau x is when there is a drag force, tau x 0. At the bottom there is no force, drag force, this becomes 0.
It is written z equal to H, where tau is equal to 0. But in the integration it is written minus H to 0. Not
Yes.
H to 0.
Yes, the integrations will be same, I guess. You can write with 0 to plus h. The integration will be same.
0 to plus H, okay.
Yeah.
Then fill it.
Yes. The integrated velocity flux, you can see is perpendicular to the direction of the surface shear stress tau s, which will be along the wind direction, and also the k cap or the z direction. Hence, the velocity flux associated with the Ekman transport is perpendicular to the wind direction, and if we multiply the flux with the suitable length scale L, suppose, may be associated with the width of the current of the ocean current that is being observed, then we get a net volumetric transport rate of what? In the mixed layer, due to the wind shear effect. This effect is called the Ekman transport and is also perpendicular to the wind direction. So you can check the vertically indicated Ekman velocity flux is perpendicular to the direction of wind shear. Is perpendicular to the wind direction. So V is coming from the cross of tau s, and tau s is proportional to the wind direction. This is proportional to wind. Direction. Note that wind shear is along the direction of wind, hence the net Ekman transport is perpendicular to the direction of wind from the cross term. The relationship between wind direction and surface current and the net water transport flux directions have been shown in the first figure. Here in this figure you can see cyclonic and the anticyclonic wind circulation tend to cause the net transport of surface water away from or towards the center of circulation respectively. In the northern hemisphere, when there is a cyclone, there is a low pressure front here and high pressure here. Due to low pressure, the surface water, the level would be diverged here. You can see the surface will go down, becomes convex, but at the high zone, there will be this level will be high. The similar opposite thing will be when in the central there will be high pressure zones. It will be a concave kind of. It will just go up. It will upwell the ocean water. So the cyclonic circulation tends to transport the surface water away from its center, and the anticyclonic circulation tends to bring the surface.
It's not clear, ma'am, why it is against the gravitational force.
Yes.
For anticyclonic.
Yes, tau s and k cap. This tau s is the direction of the wind, and the directions perpendicular to wind direction you have to consider. So this tau s, you can figure out what will be the tau s direction here in this figure. So sorry, the tau s will be
for clockwise, sorry, this is, and for anti-clockwise rotation it is showing divergence, but for clockwise showing that convergence.
Yes.
Convergence of CO2. But both are creating thrust on the surface. So why one is divergent and one is convergent?
Yes, that is the also the thing. Yes, I have to be clear with this picture again. Okay.
Okay.
Yes, I will have to find the direction of tau. You can just go with the direction of tau s in this figure. How will be the tau s in this figure, and then figure out. Then we will discuss this in the later class.
Okay, ma'am.
Okay. The circulation around the low pressure in the northern hemisphere We know it will be anti-clockwise and drive the water from the center to the edges of the wind system. This will cause a local upwelling and the thinning of the mixed layer at the center. The circulation around the high pressure system will cause a reverse effect. In the southern hemisphere, both wind direction and the direction of the oceanic transport are reversed. Hence, the net effect is same. The cyclonic and anticyclonic circulation play an important role for upwelling and downwelling of ocean water. And in the when there is a cyclonic circulation, the ocean water bends and there is a downwelling of water in the center in the cyclonic time. But in the anticyclonic time, there is an upwelling of ocean water in the center and the downwelling in the outer region. We have to figure out the wind trace, this wind trace vectors and the k cap and the tau is how behaves. Near the equator, the geostropic balance equation, we cannot figure out the tau is today. Near the equator, the geostropic balance equation no longer hold good and the frictional effect becomes important in balancing the equations for the wind directions. The Ekman transport will also be no longer perpendicular to the wind direction, because here at the f tends to 0, you know phi tends to 0, sine phi tends to 0. The direction of Ekman transport near the equator for the easterly wind is shown below. It is seen that the Ekman transport is along the wind direction at the equator, but begins to be angled away as we shift from the equator, and eventually it becomes 90-degree with respect to the wind direction at 10-degree or the northern or southern latitude. But we see from this figure in the left side that the easterly wind will cause a divergence of surface water away from equator, which will cause local upwelling and thinning of mixed layer. In contrast, westerly wind will cause convergence of water at the equator and will cause a downwelling of corresponding thickening of mixed layer. So the key points in this figure are the easterly wind is cause the divergence of surface water away from the equator, which causes the local upwelling and the thinning of mixed layer. In contrast, westerly wind causes convergence of water at the equator and causes the downwelling and the corresponding thickening of mixed layer.
Excuse me, ma'am.
Yes.
I could not understand convergence. Divergence part is okay for easterly wind, but for westerly wind, how it causes convergence?
Yes, so we have to be more careful here. Convergence means there will be more water will be coming there. So, is not it?
Yes, but how?
Okay.
Westerly means the wind flow in the opposite direction of easterly.
Yes.
But it is again in the horizontal direction. Then how convergence effect comes?
Here the westerly and easterly wind are not in the same.
Both are in opposite direction, but
Okay. Okay, I have to be more clear in this part also.
okay.
Okay, I will try to answer this in the next class. This two thing I will answer in the next class. Now the next thing we will solve few MCQ with this discussion today, and the rest will be discussed in the next class. So the first MCQ is question 17. Ekman transport is oriented at which angle to the wind in the northern hemisphere? 0 degree for 45-degree right, 90-degree right, 90-degree left. Ekman transport is oriented to what? Angle to the wind in northern hemisphere. 0 degree, 45-degree right, 90-degree right, and 90-degree left. Ekman.
45-degree right.
No, this is 90-degree right. Ekman transport is oriented
90-degree.
90-degree and the right direction in northern hemisphere, and for the southern 90-degree left. For the Coriolis parameter, 2 omega sin phi at equator f tends to 0, we know. Question 19 is Ekman spiral rotates which directions? Clockwise in the depth of northern hemisphere, anti-clockwise in northern hemisphere, independent of hemisphere, and none. With the depth of the mixed layer, the Ekman spiral rotates clockwise with depth in the northern hemisphere. Question 19, option A is correct. The unit of Sverdrup in SV is what?
Option B.
Yes, this is option B, meter cube per second. Question 21, cyclonic wind circulation in the northern hemisphere causes what? Downwelling, upwelling, what?
Downwelling.
Yes, question 21, option A is correct. Question 22A, anticyclonic wind in the circulation in the northern hemisphere leads to the downwelling and thickened mixed layer.
False.
Yes, this is false. This is caused the upwelling and the not thicken, the thicken. Question 22, at equator, easterly cause convergence, that is upwelling.
False.
Yes, question 22 false. Question 23 no. 23 and 24 live for today. Question 25. Just discuss question 25. Deep ocean circulation is mainly driven by the temperature gradient. Is this statement true or false?
I think it is false.
Yes, this is false because temperature and salinity both determines the deep ocean circulation.
Yes.
Question 26. Proxy for the water mass H is dash saturation. Proxy for water mass H is oxygen saturation. Next, I should discuss this now. So large subtropical high pressure center, we know that exists between 20 to 30 degree latitude, corresponds to the descending branch of Hadley circulation system. Because we know that in the equator there is the upward branch of the Hadley cell and lower branch of the Hadley cell is at the 20 degree to 30 degree latitude. This pressure belts leads to the formation of large subtropical anticyclonic circulation in each ocean basin centered at around 20 to 30 degree latitude. This anticyclones drive clockwise wind circulation system. between low and the mid latitudes in the northern hemisphere, and an anticyclonic wind system in the low and the mid latitudes in the southern hemisphere. The equatorial easterlies, or known as the trade winds, and the mid latitude westerlies are the low and the upper arms of the anticyclonic circulation system in the ocean. This causes the near surface waters at this region to also generally move in the clockwise pattern in the northern hemisphere and in the anti-clockwise pattern in the southern hemisphere. These circular flows of water are known as gyres. This has been shown in this figure. The different gyres has been shown in this figure. This circular flow means that water near the surface water from the tropics move to the high latitude through the western edges of the ocean basins or the eastern edges of the continents, while the cold water from the high latitudes move toward the equator along the eastern edges of the ocean basins or the western edges of the continents. This circulation occurs in between 25° to 55° latitude. The presence of cold oceanic waters over the western edges of continents minimizes evaporation and cool the surface air there. This results a cold and dry climate with the high atmospheric stability along the western margins of the continent. Here the cold circulations in the oceans has been shown with the blue color, and the warm circulations of the ocean water has been shown with the red color, you can see, and this is prevalent in the mid latitude also region only. For the example includes the east coast of the North and Southern America, east coast of Asia and Japan, and the east coast of Australia. The cyclic circulation causes an effective Ekman transport of mixed layer water towards the center of these gyres, as the transport direction to be 90° with respect to the surface level currents, as discussed previously from the Ekman transport slides. This surface waters are displaced from the edges of the continent and moves towards the center of the gyres. This results upwelling of deep layer waters near the continent edges, particularly where we have long stretches of meridionally oriented coastline. Strong upwelling is observed primarily in the western edges of Northern and the Southern America and the western edges of Northern and Southern Africa. Upwelling of cold currents on the western edges of this continent further generates the cold and the dry weather on the western coasts, creating the dry arid deserts there. For the example, Atacama Desert in the coastal Peru and Namibia Desert in the southern Africa. And the Coriolis effect is absent near equator, and hence easterly winds tends to drive the surface current westward here. As they travel to the surface, these equatorial currents warm up by absorbing the strong equatorial solar irradiance, particularly in the Pacific where the oceanic basin is white. When this warm equatorial currents arrive in the coastline of Indonesia or northeast Australia, they promote evaporation and formation of the atmospheric instability. Thus, warm, humid and wet conditions prevail over Indonesia along with the coast of the northeast Australia. Now the two small questions are we can solve. The western boundary currents, that is Gulf Stream, carry what? A cold water equatorward, warm water poleward, saline water downward.
Option A.
Yes, option A is correct. Question 24. Eastern boundary currents, that is Peru current, causes cold, dry, stable climate. Is it true or false? This is true. because in here
Yes.
at the western of South America, there is the cold region is cold dry current here. The western edges of continent further generates cold and the dry weather on the eastern coast, creating dry arid deserts, upwelling due to the cold upwelling of cold currents on the western edges of the
Peru
continent.
current, I was not understand Peru current. That's why. Peru
Okay.
current. This is called Peru current.
I guess this current is Peru. Sorry, we have to be more careful. Yes, we will discuss this Peru current if the time permits. Okay. Okay. Now the next question. Question 28. There is no major deep water formation in Pacific at this as the fresh water surface water suppress sinking. Is this true or false?
False.
Question 28. This is true, I guess. You can check the notes here. Question 27. Main site of global deep water formation is North Atlantic, North Pacific, Indian Ocean and Equator. Main site of global deep water formation is what? Main site of global deep water formation is North Atlantic. Uh, Question 29. Antarctic bottom water forms due to warm plus salinity decrease from sea ice. Is this statement true or false? We have not discussed this. Just leave this.
I think we will discuss in the next class.
Yes, yes. We should. Yes, I am stopping today at 28. We will discuss the
Thank you.
next question in the next class. Thank you for joining. Yes.
Thank you.
Any other questions?
No, ma'am. It is very clear.
Okay.
Everything.
Okay. Thank you.